Alright, hey guys, I'm at jury duty, so I just want to do a little mini lecture on intermolecular forces. So hopefully the demo that I so skillfully recorded has worked out pretty well for you guys. So I want to talk about that for just a quick second. First, we have three definitions. So I'm going to define polar molecule. Look. Let's see, what were the other two? Non-polar molecule. And intermolecular force. So if you guys haven't already, you should be opening up the intermolecular force worksheet, and there's a little chart that you should be writing these down in. So, polar molecule. Let's think for a second. What do we think of when we hear the word polar? Anyone? All right. So yeah, me too. I think of like the Earth, and it has its two poles. So here's our Earth, North Pole, South Pole. So polar actually means two sides. So a polar molecule has two sides, one with a positive charge and one with a negative charge. Some examples of this are like, let me actually give you some examples. So polar molecule with two oppositely charged sides. And I have talked about this a little bit with water molecules. So when we look at a water molecule, for example, you have hydrogen, oxygen, hydrogen. And of course, I need to remember my lone pairs. So a water molecule always kind of looks like this Mickey Mouse, like this, where these are the hydrogens, and this is the oxygen. So if you look, all of the electrons are pretty much around this oxygen, right here on this side. Let me try to draw it again. The hydrogen has its proton, which is a positively charged nucleus, and then its two electrons are being shared with this, or one electron is being shared with oxygen. And here's the other hydrogen, and then here's the oxygen. So on this side, there's really no electrons, and on this side, there's a lot of electrons. So this would be a molecule with one side that's negatively charged and one side that's positively charged. So this side, this is like this a weird Greek letter. I'm going to draw this. It means a partial charge. So I'm going to write a plus, and this side has a minus. And we're actually going to talk about this next class, either via webcam cast, or hopefully I'll be there in person. But it's called a polar molecule, and it has these what are called dipoles. So di meaning two, poles meaning opposite ends. So we got the positively charged end and the negatively charged end. So water is one of those molecules that's very polar and can attract to itself other different water molecules. Another example would be like hydrogen fluoride. We got HF. Again, fluorine wants all the electrons, and then the hydrogen is kind of like this exposed proton out on the other end. So here's the two electrons, and here's the fluorine. It has 6 other ones. So which side would be positive and which side would be negative? Here's a tip. Hydrogen is always the positive side. So plus, minus. Pretty easy. So that's a polar molecule. So a nonpolar molecule is simply the opposite. Nonpolar molecule would be molecule with no difference in charge. Basically, there's no part of the molecule that's stronger than the other part. So there's a couple different ways you can have a nonpolar molecule. one way is if the molecule is uniformly strong, like F2. You just have electrons on both sides. And one is if you have a uniformly weak molecule, like H2. Here's the hydrogen sharing with another hydrogen. It's symmetrical on both sides. The other way is if your whole molecule is just made up of carbons and hydrogens and things that aren't really that strong at attracting electrons. So oil is a really good example of a nonpolar molecule. Ethane, ethanol, anything where it's like C2H6 or C8H18. Anything with carbons and hydrogens is going to be a nonpolar molecule. And that's because these molecules are just, here's like carbon. There's no one area that has more electrons than another area. So there's no one place that's going to have a partial negative charge, and then there's no one place that's going to have a partial positive charge. As you guys saw, hopefully, when you did the oil and water experiment, and when you tried to attract the water to the wand, the water molecules do attract to each other. And they kind of, the positive sides, here's the negative side of a water molecule, is going to get attracted to another water molecule on the negative side. So the water molecules can kind of pull each other in the same direction. They're like little tiny magnets. Nonpolar molecules cannot do that. The third thing is going to be pretty obvious. Intermolecular force. Inter meaning between, and molecular meaning molecules. So forces that occur between molecules. So we're not talking about bonds here. We're talking about forces that are happening when two different molecules or two of the same molecules interact with each other. So intermolecular force, attraction or repulsion between molecules. Okay, so far so good? You have Google if you have any questions. Okay, so I hope you guys all got this written down. Now I'm going to give you the 3 different types of intermolecular forces that I'm expecting you to know. So I'm going to erase it, and then I'm going to draw a grid. So get ready for the grid. Hopefully I don't actually get called for jury duty, but you never know. So I'm going to write 3 types. Okay, so this is going to be the strongest type up here, and this is going to be a weaker type. The first type it has a tricky name. It's called hydrogen bonding. So okay, so I'm writing type of IMF. IMF means intermolecular force. So the first type is actually called hydrogen bonding. And there's a big caveat here, because this is not a bond. Not a bond. Hydrogen bonding. Not a bond. And this is the type of bonding that you see in water molecules. Since hydrogen is really just an exposed proton when it's bonded with something else, it can create the strongest type of intermolecular forces because that proton just has a partial positive charge. So anytime you have a hydrogen and certain types of molecules, it will have this, what's called hydrogen bonding. So the description is bonds between hydrogen and either fluorine, oxygen, or nitrogen. So, three types of intermolecular forces, starting off with hydrogen bonding, not a bond. So, description, bonds between hydrogen and either fluorine, oxygen, or nitrogen. And then I wrote in parentheses, it's FON. That's how I remember it. It's FON. Fluorine, oxygen, nitrogen. And what that looks like is you have, just like I was showing you, the water molecule, oxygen, hydrogen, hydrogen. And like we know, this is going to be the partial negative side, and this is going to be the partial positive side. So that's going to be attracted to another water molecule. And then this one will get attracted to another water molecule. So the hydrogen bonds, a lot of times, are just little dotted lines. So that's a hydrogen bond. That's a hydrogen bond. So it's the forces that attract one molecule to another only when it's between hydrogen and either oxygen, fluorine, or nitrogen. So hydrogen bond right there and right there. It would also work between NH3 can have hydrogen bonds. HF can have hydrogen bonds, and those are the guys that we say that have hydrogen bonds. This is the strongest type of intermolecular force. The next strongest type is called dipole-dipole. It's fun to say. Everyone can say it. Dipole-dipole, dipole-dipole. So, dipole-dipole forces are like hydrogen bonds, but they don't have to be between hydrogen and either fluorine, oxygen, or nitrogen. So these can be attractive forces between polar molecules. So what's an example of a polar molecule? Well, it's any molecule that's going to have one side that's a little bit stronger than the other side. So let's think about, technically, hydrogen bonding is a type of dipole-dipole force, but since it's so much stronger, we give it its own name. But I'm going to think of a different type of polar molecule. Let me think about, I don't know. CHCl3. We got chlorine, hydrogen, hydrogen, CH3Cl, hydrogen, chlorine. So carbon, chlorine, hydrogen, hydrogen, hydrogen. Which side is going to be the positive side? The hydrogen is, of course. And this chlorine is going to be the negative side. So this will come into contact with another similar molecule, and this side is going to get attracted to the hydrogens. And they just kind of line up. And then this chlorine is going to get attracted to some other hydrogen sides. I don't even know if you guys can see that. So it's very similar to the hydrogen bonding. There you guys go. Very similar to hydrogen bonding, except you don't have to have it be between hydrogen and either fluorine, carbon, or oxygen. This is just any molecule that's got, this is like a very rudimentary drawing. It's got a positive side and a negative side. The negative side is going to get attracted to the positive side of another thing. Oops, that's negative. And so on and so forth. So dipole-dipole is like those partial charges. Okay, now my favorite one. This one is just called, the weakest one is called dispersion forces. Oops, weak. And you guys are actually going to have to get out of your seats for this one. It's going to be fun. Okay. Weak. I wish I could be there to do this. We're going to have to choose someone in each class. Maybe the sub will do it. So dispersion forces happen between non-polar molecules. So they are temporary dipoles between non-polar molecules. Okay, so what is a temporary dipole? So let's think about it this way. Say we've got C2H6, a nonpolar molecule. It's got carbon, carbon, hydrogen, 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 hydrogen. Okay? And the electrons, are they actually just only right here and here, only right here and here, only right here and here? Do they stay in one spot the whole time? No, of course not. They're zooming around at the speed of light randomly. So the electrons are all zooming around, zooming, 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 zooming. And at any one point, there might be more electrons on this side than at the other for just a split second, and then it's gone. And then at another point, there might be more electrons on this side than the other. And so I'm going to ask you guys to do something as a little demonstration. So we're going to do the wave. Okay, you know, like in stadiums, how you do the wave. So I want one person to go to one side of the room, and then you kind of, as they run in front of you, you're going to do the wave and then go back down. Can you guys do that for me? Okay, I'm going to time for 20 seconds and while someone does the wave. Do it one direction and then the other. All right. I know you guys are doing it. All right. Hopefully you did the wave. If not, please pause this video and do it. Basically what happens is your arms are up for a second and then they're back down. And that's what these molecules are doing. The electrons are here for just a tiny, tiny split second, and then they're gone again. And then they're back, and then they're gone. So, because they're all zooming around randomly at the speed of light, the odds are at one point you're going to have more electrons on one side than the other. So, these guys get these temporary dipoles. So, it's like, for one split second, you're going to have a positive charge on this side. And for the same split second, you're going to have a negative charge on the other, depending on where the electrons are. All of the molecules are like that. So this guy is going to just very, very briefly be attracted to another molecule. Very, very briefly, and then it's broken, and then it's there, and then it's broken. I hope that sort of makes sense. This is kind of what oil is like. If you guys remember, you put a water droplet on a wax paper. So this is wax paper. You put a water droplet, and it kind of makes this giant bubble. And the reason it can do that is because the water molecules are all attracting to each other, and they can kind of hang on to the other ones, when really you would expect it to fall flat. An oil molecule, or an oil droplet, you put it down and it spreads out super, super flat, because it only has dispersion forces. The reason you know there are dispersion forces is because when you pour it, the molecules don't fly everywhere. They still stay in a puddle. It's a very, very flat puddle, but they don't completely dissipate. So hopefully that makes sense. I'll post this video on Moodle. You guys have your definitions, and now you're going to learn about geckos. Yay! See you guys Thursday and Friday.